Hello, let's continue to study the absolute convergence in 11.6. So let's take a look. Firstly, I'm going to give you the definition for absolutely convergent, okay, or absolute convergence. Definition 1. A series AN is called absolutely convergent. So let's see. If we take the absolute value of all the terms AN and we get a new series, if the series of absolute values we write down like this way, right? If this is convergent, we say the series absolutely convergent. Okay, now let's take a look at some examples. Let's take a look at the first series, 91 to the n minus 1 over n squared. And from the series, we know this is the alternating series, positive, negative, positive, negative. And let's see, this is absolutely convergent or not. Now, if we take a look at our absolute value of all the AN, that means we take the absolute value of all the terms. In this way, when we take a absolute value to all the term and the negative 1 to the power, this equals positive 1, negative 1, it will always be 1. So you just make this into 1, right? Will go away. So it's just like 1 over n squared. Because n squared is positive, you don't have to put an absolute value there because it's always positive. Okay. Now this is the series when we take the absolute value, and we noticed this is P series. Actually, this is P series with P equals 2, and the series convergent. Okay, so our series, the original one, the alternating one, is absolutely convergent. Okay, something like this. Now let's take a look at the second problem. We can try the exercise problem here. And from 1 to infinity. Do you still remember what do we call this series? We call this series alternating harmonic, right? Okay, and in the alternating series section, we use this alternating test. We test this series and we know this converges, right? But let's take a look at the absolute value of this. Same thing. When we take the absolute value, the negative 1 to the n minus 1 go away, so just 1 over n. And this become harmonic. We know harmonic series diverges. So this alternating harmonic is not absolute convergence, right? So we can say it's not absolutely convergent. Okay, so that's the exercise problem. But you know, for the exercise problem, we call this case conditionally convergent. So what's the conditionally convergent? If the series is convergent itself, but is not absolutely convergent, which we call that conditionally convergent. Let's take a look at the definition too. It's called conditionally convergent if it is convergent but not absolutely convergent. That's the definition for conditionally convergent. Conditionally convergent means still convergent, just not absolutely convergent. We can take a look at this series. Can you tell this series convergent or divergent? You know, this is an alternating series. By using the alternating test, just to remember the test, we have three conditions: un positive. So for this case, un is 1 over root n, right? Positive. And the second case, decreasing. This is decreasing when n large, un becomes small, right? And the third, does un goes to 0? The limit, yes. So actually, this series satisfy those three conditions. This is convergent. Okay, but let's take a look at the absolute value of this thing. Okay, this becomes just 1 over root n. This is p series with p equals 1/2. We know this diverges. So that means this series is not absolute convergent, but it is convergent. So this is conditionally convergent. Right. Okay. We can say this is example 2. Let's take a look at the next theorem. If the series absolutely convergent, then it is convergent. Let's see. If we say this is absolutely convergent, then it is convergent. We skip the proof. The proof used the comparison test. So it's kind of like a an plus this less than 2 absolute value of an, because this is absolutely convergent and less than convergent. So this series convergent, and this equals an plus let's see minus. So this difference of two convergence series is also convergence. That's the proof. You don't have to know this. Okay, we can skip this part. Now let's take a look at the example, how to use this theorem to tell a given series convergence or divergence. Example 3. So test 91 to the n cube 3 to the n for convergence. And start from 1 to infinity. Okay, let's take a look at this one. This is the alternating series, right? Okay. Let's try to use absolutely convergent theorem to test the convergence for this series. Now let's take a look. We take the absolute value of this series that become n cube 3 to the n. Because this section, is ratio test, also has a ratio test and root test. So here I want to review the root and the ratio test with you. So I'm going to use two methods to tell this is absolutely convergent or not. So now let's see. If we use the ratio, just a little review, but you can use other tests to say this convergent or divergent. Ratio test, that means an plus 1 over an, and because we take an absolute value, and it becomes, so we don't, when we take the absolute value, we don't have the -1 anymore, it's just n plus 1 cube 3 to the n plus 1. This is a n plus 1 absolute value, and divide by a n absolute value, that is just multiple by this. Simplify, this cancel with that, 3 left. So after we simplify, we get this, right? And because this part, they have the same power, actually the limit will goes to 1. So the whole limit goes to 1/3 less than 1. The ratio test means when the limit of the ratio is less than 1, then the series converges. Okay, so that means this converges, and that means our series is absolutely convergent. And if it's absolutely convergent, then we just say this convergent. Okay, because if it's absolutely convergent, then it is also convergent. That's the ratio test. Now let's review the root test. Same thing, we use the root test to this. Okay, so when we take the nth root of the absolute value of an, that means just n cube over 3 to the n, because -1 go away. Okay, oh, I can say, write down one more step here. Absolute value of an, and simplify 3 to the n, and the nth power is taken out because 1/3, and on the top is going to be nth root of n cube, and this is n to the 3 over n power, and the top actually is n to the 1 over n third. You can skip this step, but the numerator goes to 1. In the sequence section, we learned the limit of this. This is one of the commonly used limit. And the whole thing goes to 1/3, which is also less than 1. In this case, same thing. This convergent. So an absolute convergence, then convergence. Okay, so this is how we use the test absolute convergence test. Let's take a look at the exercise problem. Very similar, but a little bit different. Just, you can try this by yourself. And I'm going to give you the solution to this. I'm going to, by looking at this series, I think it's easy to use power root test to the absolute value of an. So let's see, I'm going to simplify this a little bit because I know I can separate 10 to the n plus 1 power into 10 times 10 to the n. So you can see this has n power, that's why I like to use root test. Okay, now let's perform this. Becomes nth root of negative go away, 10 to the n, and this equals, simplify, we can take the 9 over 10 out, right? And nth root of 1 over 10n, and 9 over 10 here, 1 over 10 to the all times n to the nth power. Okay, let's do a little bit detail. So 9 over 10, 10 to the 1 over n to the 1 over n. Actually, those two, they both are commonly used the limit, and they all goes to 1, goes to 1, goes to 1. So the whole limit goes to 9 over 10. And we notice that 9 over 10 is less than 1, and we know less convergence, and this is absolutely convergent. Then it's convergent also. Okay, so this is the exercise problem. This is all about the absolute convergent or divergent. Now we can stop this section.